Okay, so I want to start talking about collision. It's not going to be an easy explanation because some things need to be understood for this all to make sense, because it's kind of confusing the way this particular method of collision detection is set up. So what happens is we take a bit and assign that value to a single tile on screen to tell whether you can pass through it or whether it's solid and the player collides with it. So since there's 32 tiles wide on the NES, you would have 32 bits in a row. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 1, 2, 3, 3, 4, 5, 6, 7, 28, 29, 30, 31, 32. It would look like this. You have 32 bits wide, and then however many rows you have. And the NES has 30 rows. So bits can't be stored in this huge long manner, so you have to divide this into bytes. So 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. So we end up having 32 tiles wide equaling 4 bits wide. So what our collision map in our ROM looks like is 30 rows of 4 bits wide. So this continues on for 30 times. Now the tricky part comes into, let's say we have one of these rows is floor. How do we actually index into this array in such a way that we get individual bit values? So let's actually just first explain how to index into a 1D array. So the formula for this is going to be the x position plus y times the width of your array. So let's imagine not an NES screen, but just a theoretical game system that is 10 tiles wide and it's 4 tiles tall. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And let's say there's floor on this row. 2, 3, 4, 5, 6, 7, 8, 9, 10. And more floor. So this is our collision map. Just to theorize. Now we want to convert our x position and our y position to index into this array. So let's imagine that our x and y positions are already in tile space. In reality, the NES, the x position and y position are the pixel position on screen. So we're going to have to deal with that later, but for the sake of argument, let's say that this is tile space. And let's say our player lives here. He's standing on the ground. So he is 0, 1, 2, 3, 4, 5, 6 tiles over. His position is 6 in the x-axis. And then how many rows is he? So here's the 0 row. Here's the 1 row, 2 row, 3 row. So he's on row number 1. So we'll say y equals 1. So let's use this formula. Let's say x is 6 plus 1 times 10. So that would be 6 plus 10, which is 16. Because what the computer sees is it doesn't see this 2D grid that we've conveniently written in our text editor to help visualize what the space looks like. All it sees is this. It sees the first row. It sees the second row. And it sees floor and it sees floor. So this is actually how it's stored and how the computer is reading it. So we have to be able to index into that using this formula up here. So we've calculated from our x and y position that the player is in position 16. Let's see if that's true. So we count 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. The player is indeed in position 16. So that is the simple explanation of how to index into a 1D array. But our 1D array is a lot more different. It's not 1 bit per index. So each one of these bits lives inside of a byte. And the index will only index into the byte space. So we have to do a bit of tricky math with our X and Y location to deal with indexing into byte space and looking up the bit position with a lookup table, and dealing with converting the X position from pixel space to tile space. So here's what I mean. Let's actually explain the converting from pixel space to tile space. So imagine that these are your tiles on screen. There's 32 of them wide and there's 30 of them tall. Each tile on screen is divided into 8 pixels. So there's a 0 pixel, a 1 pixel, all the way up to 7 in the X direction and the Y direction of each one of these tiles. So 32 tiles times 8 pixels each, that's 256 pixels wide. That's the resolution of the NES. So the X location of your sprite, that value is an 8-bit value, and it's stored as 8 bits, and it's counting a 256 valued number. So when your player position is in the very left position, that number is 0. When it moves over 1 pixel, that number increments to 1. Another pixel increments to 2. Another pixel, it increments. It increments, and as your player moves across the screen, that number is incremented. Now, we don't care what pixel that player is on when they're inside of a tile. We just care if they're inside of a tile. So let me label these bits in a specific way to help us visualize which numbers of this value that we care about. So the lower 3 bits, we're going to call that pixel space because it takes 3 bits to represent 8 positions. And those 8 positions correlate to each pixel inside of a tile. The upper section, we're going to call tile space. So every time 8 pixel positions has been traversed, these 3 bits overflow and ticks 1 value in tile space. So now with these labels on screen, now let's watch the pixel move across screen. This is our player position. So we're going to move right, we're going to move right, and we don't care about these lower 3 bits because we are still in the same tile. But look what happens when we traverse the border. Pixel space overflows and we tick 1 up in tile space. And you can see with my little labels behind here, we have tile 0 and we have tile 1. If we ignore pixel space and look at the X position in terms of what tile we're on, they correlate. So we're in the first tile, which is the second one over, and that's true. So our little pixel guy is in that tile space. So if we then keep traversing, that pixel space will count up, and we don't care about it. And now when we actually traverse over to the number 2 tile, bam, tile space gets updated. So in reality, in our code, we're going to have to divide the X position by 8, and that is truncating these 3 bits off because we don't care about them. And we do the same thing to Y. So let's update what that looks like. So that formula was X plus Y times width. Now we know some of these values already because remember, our bitmap is going to look like this. 1, 2, 3, 4, 5, 6, 7, 8. 2, 3, 4, 5, 6, 7, 8. 2, 3, 4, 5, 6, 7, 8. 2, 3, 4, 5, 6, 7, 8. So we have 32 bits in a row, which is equal to 4 bytes. So our width is 4. Now let's account for converting from pixel space to tile space. So X is divided by 8, and Y is divided by 8. Okay, so this is our updated formula. We're not all the way there yet because we've run into a similar scenario. So now that we're looking at the character in terms of where they are in each tile, so let's say the character is in this tile. Let's say he then moves to this tile. Let's say he then moves to this tile. They're still traversing in this byte space, so he's in this byte. So when we have to have a lookup index, that index needs to stay the same, while the index into what position he is within the byte needs to get updated. So let's explain that in a better way. So just like we did with converting pixel space to tile space, let's look at our tiles on screen. We have 32 tiles wide, 30 tiles tall. And let's say we have our bit mask. So it's 32 bits wide, and it's 30 rows of those bits tall. So our array is only 4 bytes wide. And each one of those bits corresponds to a specific tile that's on screen. So to make it more visually explanatory, I'm also going to divide these tiles to tile space 1. So this is byte 0, byte 1, byte 2, byte 3. So just like we converted from pixel space to tile space, let's convert from bit space to byte space. I'm just going to go ahead and put my labels up here just the same. The lower 3 are going to be the 8 positions within the byte, and the upper 2 are going to be the position across these 4 bytes. So let's traverse. We traverse to the right, traverse to the right, traverse to the right, traverse to the right. We do this 8 amount of times, and that takes 3 bits to represent. And as we cross this border into the second byte here, into this byte, bam, byte space gets updated to 1. That correlates to the byte we're in, and then the bit space is overflowed down to 0. So in order to actually find the byte space index, so we're indexing into which byte we want to look at and care about, we again truncate 3 bits, and we do that by dividing by 8. So the x position is divided by 8 again. So 8 divided by 8 is 64. So this is the formula to find our byte index. So that's important. We need our byte index. Next, we need to figure out how to check its position inside the byte with the position of the solid tile within our bitmap. So let's say our player is in this position. Let's go back to our visual representation. What happens when they are in the first bit position? Bit space is set to 0. So when we want to check that the player is in this position, we're going to use a lookup table called BitMask, and the 0th index is going to have that value in it. And now look what happens when we move 1 bit over. So now the bit space is at 001. So at the 1 index, that gets incremented over, and it looks like this. And you want to do that to your entire index, because every time you increment, this 1 position also increments. And you do this 8 times. So 4, 5, 6, 7, 8. So every time you traverse, that bit moves over. So the easy way to find the bit index, now remember, we converted from pixel space to tile space, x divided by 8, oops, and that gave us this 5-bit number. It's in tile space. Now we only care about the lower 3 bits of that 5-bit number to actually use bit space as our index into that lookup table. So we're going to AND it with the value 7. Now what the value of 7 looks like, so 7 equals in binary this. So it's the 3 least significant bits. So BitIndex equals x divided by 8, and then use the AND operation with the value of 7 to only care about those 3 bits. And that value at the end of this equation is your index into this BitMask. And that's how you check where the player position is against your bitmap that is in this weird 4-byte wide format. So what does that look like in code? I hope that was a good enough explanation. I know this is very confusing. It confused me. That specific algorithm, those equations, I found on NestDev. There's a post by Takamaru who put those equations down. I figured them out in assembly, and I kind of used it as a black box for a while, not really understanding what was going on. But I wanted to make it a point to actually understand what was going on and why those values were, why was I dividing x by 64, why was I anding with 7, and this sort of stuff is that reason. So let's go to the assembly. So just for the sake of time, I've put in a blank collision map. So these are the bits that we can toggle on and off to actually cause collision to occur, collision not to occur. So right now all the bits are 0. Let's actually add the BitMask table because we need it. So let's go to direct byte. Let's do this 8 times. And let's put this here with the bit incrementing to the right every single index. Okay, so that's what we need in terms of just binary data in our ROM. So now what we need to do is take the player position, do that math that we just figured out on it, and store that in a routine that checks collision. So let's call this check collide. So what did we do first? I'm going to write my equations up here. So we have x divided by 64, and that's plus y times 4. 4 is our width, because we have 4 bytes per row. Sorry, yeah, per row. So we need to do this. So let's think about what happens before this is called. So I'm going to do this in player up. When we move the player up, let's check if it collides with something above it. So we load the X register with the player X position. Then we load the Y register with the player Y position. Then we call check collide. So check collide. And checking the collision is, we're going to do this essentially to set a flag, and then we're going to branch right here. Let's not write the branch just yet. Let's write our check collide function. So what happens when we check collide? So we need to take our X register, move it to the accumulator to do math with it, and the math we're going to do is X divided by 64. So to divide, you have to logical shift right. And to divide by 64, you do that 6 times. So divide by 2, divide by 4, divide by 8, divide by 16, divide by 32, divide by 64. And we want to store that temporarily. So we're going to store that in a variable called temp, and we have to add that to RAM. RAM, okay. Because we're about to add that to the next calculation. So we need to take y, so transfer y to the accumulator because we need to do math on it. And this is going to be y times 4. And to multiply, you do an arithmetic shift left, and to do it by 4, you do that twice. So multiply by 2, multiply by 4. Sorry, we missed something. We didn't convert y from pixel space to tile space. So you have to divide by 8 for that to happen. So y divided by 8 multiplied by 4. So divide by 8 is LSR, LSR, LSR. So logical shift right 3 times. So divide by 2, divide by 4, divide by 8. And then we have to arithmetic shift left twice. And that is multiplying by 4. So let me move this down. And this is times 4. Now that we have our y divided by 8 times 4 calculated, the equation says to add in that result from x divided by 64. So we want to clear the carry, add with carry our temp, and this is done. We can store this in a register to then use to index. So what index is this? So transfer it to y. This is our byte index. Remember, because this was the very top 2 bits of that 5-bit number to index into our 4-bit wide array. Next, we have to find the bit index. That index is used to look up in the lookup table which bytes match up with where the player's positioned in tile space. So x divided by 8 gives us that 5-bit value of the player's position in tile space. And remember, we only cared about the lower 3 bits when we're talking about bit space, and this is going to be used as our index into the lookup table. So that is, we use the AND operation on the number 7. So the number 7 is going to be 111 in binary, so that's going to mask out only those 3 bottom bits, and that's all we care about, is extracting those 3 bottom bits. So let's make that happen. So transfer x to a to do math on it, and this is going to x divided by 8. How do we divide by 8? Logical shift right, logical shift right, logical shift right. We do that 3 times. Next, we have to do the AND operation to the value of 7, because we only care about the bottom 3, because this is BitMask index. Okay, I hope you see where we're going with this. Now, we have 2 indexes, and we have 2 sets of data. Let's index into those and compare them. This is where collision detection is happening. So, oh, we haven't transferred that into x. We have to transfer a into x, and this is the BitMask index. So this was calculating it. We needed the AND operation, but x is where that index is stored. Okay, so we use y to load the byte we need from our collision map, index with y. Next, we compare that value that's in our collision map with the value we grab from the lookup table from where our player's positioned. So we AND it, so we're actually comparing it with only one tile at a time. So we AND it with BitMask index x, and what happens? We're going to return from subroutine, but what this AND has done is it's either set the 0 flag or it has not set the 0 flag. So let's say that our collision map looks like this. And let's say, based on the player's position, he's running into that position in the byte. So it looks like this. This would be a scenario in which they collide with the tile. So when you AND a 1 with a 1, the output is a 1. So when we use a branch instruction, we have to either use branch if equal or branch if not equal. So branch if equal is only checking the 0 flag. It's checking if the result was 0. So let's say the player was not in this position. If we AND a 0 with a 1, the answer is 0. So a break if equal means not collide. And a break if not equal would mean collide. I hope that makes sense, because if the AND operation renders a 0, that means the player isn't in that tile. So when you branch if equal, that's saying that that case was true. So they weren't colliding with anything. So let's put this is a done routine. So we can call this after we've loaded X and Y with our player position. Let's actually implement this. So we want to check when the player is moving up. We loaded the player's position, the X position into X, Y position into Y, to then check collide. We checked collide. Coming out of check collide, the 0 flag is either set or it's not set. So we want to branch if it is equal, so when nothing has collided, to skip the next command we want to have happen. So this plus is going to jump to plus, and we're going to exit subroutine, and nothing is going to have been collided with. But if we have collided, we don't want this decrement player position to be valid, so we counteract it with an increment player position. Increment Y, player Y pause. So this is ejecting the player out of the wall that he just collided with. So now we actually have to populate our BitMask or nothing's going to work. Let's render this, make sure there's no errors. Okay, no errors. So in our map, let's find where the wall is. This is going to boot up. I don't have all the rest of the bricks in like a compressed form for the decompressor to then unpack it. Let's just collide with this top wall. So the top wall is location 2, the X location is 2, and the Y location is 7. So 0, 1, 2, 3, 4, 5, 6, 7. And let's say this entire row we collide with. So this is the bottom of the bricks, of the brick wall. This should be the moment of truth. I think everything's set up correctly. So we're checking controllers, updating sprites, and then we have this check collide that is only checking when the player's moving up. And that's going to become important later on. Let's move up. And I've collided. I've collided with the bricks. That's because there's a string of 1s causing me to collide. Now I can move down because I'm not checking the collision when I'm moving down, but that's going to become important in the next video because we have to check all 4 corners of the sprite. Right now it's only checking the top left position because that's the default X and Y location. Okay, so I hope this wasn't too convoluted. I hope some of my explanations were easy to follow. I know it's a very tough subject in terms of this specific method of collision detection, but I hope you learned something, and I hope it's useful to someone out there, if not just entertaining. Thanks. Bye.